So once again, good morning everyone, and welcome to webinar on Multiphysics Unleashed, Acceleration Innovation through Simulation. So yeah, so myself Ravindra Bucherla, and I'm working as an application engineer in ARK Infosolutions Pvt Ltd. So in this particular webinar, we are going to explore multiphysics. So basically, we will be dealing with different kind of physics. So whenever we are working on any technology that might be aerospace and defense or automobile industry or any manufacturing. So we will be dealing with multiple products, and each and every product basically will involve multiphysics. Sometimes that particular product is going to withstand different kind of loading conditions. So that loading conditions might be electrical, electronics, or even the mechanical and different kind of fluid analysis as well. So in this session, we are going to explore the structural analysis and fluid analysis. So first we'll start with the structures, and so I would like to start with in this particular presentation. First, we'll go through about introduction to Ansys. What are the different tools that we have, and what kind of simulations that we can perform by using these tools. And later on, we'll go to the workflow of Ansys Mechanical. And once it is completed, we will move to the fluid analysis as well. So Ansys is a simulation software which is started 50 years plus back with a capabilities of solving mechanical problems. So earlier, in case if you want to design something, yes. So we used to generally we used to go for the conventional method of once we know what is the purpose of that or what is the application of that particular product. So we'll be having some initial design, and once we have the initial design, we may create a prototype, and once it is done, we will do the testing on it. And based upon the results, if the results are up to our expectation or up to the benchmarks, then we will go with the production. In case of any failure while testing the prototype, we may again remanufacture the part by changing the design changes. So again, we will do the testing and we will see whether the results are okay or not. So based upon that, we will proceed for the manufacturing. Okay. But the advantage that we'll be getting by using the simulation is instead of going directly to the prototype, we can apply the same loads on boundary conditions, whether it is a that loading conditions might be any structures, fluids, electronics. So whatever the loading conditions that we are going to test that particular product, so the same loading conditions we can apply in the software itself, and we can see the results. So if the results are okay, then we can go with the prototype and we can match the results and we can go for the production. So like this, Ansys is introduced multi physics basically. So as it is started with structural simulation, where it has the capabilities to solve the problems related to the strength analysis when the structure is subjected to different kind of loads and boundary conditions. And over the period of time, it integrated different physics like okay. So as we know, for the explicit dynamics like impact crash, that kind of simulations, we have LS-DYNA tool, and Rocky for the particle simulation, Fluent for the fluid dynamics. So like that, over the period of time, it has integrated many other tools which will support different kind of equations to solve our problem. And now, yeah. So now we have. Okay, so like that, by using all these tools, whatever the challenges that we'll face while developing a new product or new mission. Okay, so instead of directly jumping into the prototype, we can solve the challenge by using the simulation software. So by doing that, we can accelerate our product to market. So instead of doing repetitive work in the hardware, like by using the physical prototypes, if you test again and again, it will take a lot of time to develop the complete product. So by using the simulation, we can accelerate our product to market. And also, in case if you want to go for different kind of optimization, like suppose we have an initial design, And instead of a single design, if you want to go for some 50 samples or 100 samples, to build the prototype and to test the prototype, it will take a lot of time. But by using the simulation, even we can innovate the product by doing different design changes, or even we can go for different optimization methods, and we can innovate our product. And overall, it will reduce our product development cost and product development time as well. So, yeah. So this is the complete Ansys product portfolio where we have different tools for different kind of simulations. So all mechanical, whenever we are developing any mission or any equipment, if we have any loads and boundary conditions related to the structures, so these are the different tools that we will be using. And similarly, if we have any challenges that we will be facing of both structures and fluid interaction, or even if you want to analyze the complete fluid dynamics. So these are the different tools that we have available for the fluid dynamics. And whenever we are working on the electronics parts, so sometimes we will be working on electric motors, antennas, or electric vehicle. Okay. So even for electrical and electronic components also, we can do the simulations by using the electronic tools. And so these are the major physics that we have to solve the problems related to different physics. And similarly, in case generally whenever we perform any structural analysis, we might need the material properties for that particular assembly. So in order to take the material properties, we might know, like if we are using any standard material, we can directly take that material properties inside the solver itself. But in case if we are working on the advanced materials, or sometimes we know what kind of product we are going to work, but for that particular product, we are not sure which type of material will be more suitable. So in that kind of cases, we will go with the Granta. So Granta is a material database where we will be having 4,200 plus materials based upon the kind of application that we are using, and by keeping some constraint. Out of this 4,200 materials, it will automatically suggest different materials which will be suitable for that application. And so even if you know the material, sometimes we might not know the material properties which is required to calculate the mechanical properties, like Young's modulus, Poisson's ratio, density. So these all kind of properties also we can take from the material section. Okay. So similarly, we have different tools to optimize the initial design, like OptiSlang, or if you want to publish an application in order to repeat the same workflow for different kind of inputs, and if you want to get the output. So we have the Minevera and Model Center. Okay. So like that, even we can solve the different physics like photonics, optics and VR, and Gmax for designing the lens, or to see the like to work on the to work on the numerical. So these are the different tools that we have. And so these are the embedded systems tools, and this is the digital twin where we can create a twin of our original models by creating a ROM, and we can integrate the simulation results with the test results by taking the sensors data. And so similarly, we have the semiconductor domain as well, where it will be useful to solve the problems of semiconductor. So this is a complete Ansys product portfolio, and so I will just give some brief introduction about the structures, what are the tools that we have, and what kind of applications that we can solve by using each tool. Okay. So as we know, whenever we are working on any structures, we will be dealing with different kind of loads and boundary conditions. So sometimes we will be solving a problem where we need to consider the static analysis, like where there is no time dependency with respect to with respect to motion. There will not be any motion, or even the loads are not varying with respect to time. So these kind of conditions we will solve sometimes, which we will call it as a static analysis. And sometimes we will be like our product will be subjected to different kind of dynamic conditions. So that might be a vibration, or a kinematic behavior, like if we have a complete assembly, so few parts will be rotating with respect to another parts, and where we want to analyze joint reactions, forces. Okay. or sometimes we'll be having the problems which are related to you know explicit dynamics where the nonlinearity is too high, like the breakage will be too high, or the failure will be too high. So like that, in structures we'll be having different kind of applications. So for each kind of applications, we will be using different approach to solve the problem. So for that purpose, here in our Ansys, we have different tools for different kind of problems. So Ansys Mechanical and LS-DYNA is one of the flagship solvers to solve the problems related to the implicit and explicit dynamics. Okay. So basically, you know, if you have any component where we are applying force, movement, pressure, and if you want to analyze the strength of that particular part, like in which area we are having the maximum stress and in which area we are having the maximum deformation. So all that kind of strength analysis can be performed by using ANSYS Mechanical. And even if there is any vibration, so that vibration might be because of some motor or IC engines, or because of the wind loading conditions, or even the vehicle which is moving on the road might also get different kind of vibration. So whatever the vibration source that we have, so because of that vibration source, if you want to analyze the strength of the part, so like that all kind of problems can be solved by using ANSYS Mechanical. And similarly we have LS-DYNA, so which we generally use for explicit dynamics. So explicit dynamics are the cases where we will be having the failure will be too high, and this complete event will be happening within a very short duration of time, like car crash analysis, seat belt analysis, or bullet impacts, explosions, blast. So these kind of events where the time duration will be very less and the failure of the components or the assembly will be too high. So this kind of events will be solved by using ANSYS LS-DYNA. And similarly, whenever we are working on any manufacturing operations, like especially the sheet metals, so if you perform any blanking, forming, stretching, so these kind of operations, if you perform, in some areas we will be having the maximum thickness, and in some areas we will be having the minimum thickness. So in order to analyze the thickness variation across the geometry, or if there is any chance for failure in any particular area when we are performing this kind of sheet metal operations, so these kind of applications can be solved by using ANSYS forming. And similarly, not only a single component or assembly. So even we will be having a complete mission, like a complete vehicle. So where we will be performing the kinematic behavior of that particular mechanisms. So how that mechanism is going to work. Suppose in this case, if we take this excavator as an example, so basically this will be, picking load and placing load, like if it is digging the soil and loading and unloading that soil into some tracks. So while doing this operation, if you want to check what are the joint reaction forces, joint torques, moment that is required, or if you want to select any one of the part, and if you want to see what will be the stresses that are generating on that particular part while we perform this kind of operations. So like that kind of complete assembly we can consider, and we can see how it is operating, whether it is having any constraints, or the mechanism is working fine. In case if there is any component which is going to fail, so what is the maximum stress? So all this kind of multi-body dynamic analysis we can perform by using ANSYS motion. And so similarly, in case if you have any, if you are designing any electronic components, like suppose if you take PCBs, so in PCBs, we will be having multiple components like small resistors, capacitors, semiconductors inside the PCBs. So whenever these electronic components are subjected to different kind of mechanical loading conditions like vibrations or drop test, or thermal heat conditions. So if you want to know, because of these external loading conditions, what will be the life of the parts? Okay. So how long that particular components will be working well, and like at which particular time like the product is going to fail. So that kind of reliability analysis we can perform, especially for the electronic components, by using the Sherlock. And so when we talk about the advanced manufacturing technologies, so in case if we are performing any additive manufacturing, like if you are going to print any part by using 3D printers, especially the metal 3D printers. So to print a single component, it will take at least 2 to 3 weeks, generally, especially for the metal 3D printers. So once we print the part by using these metal 3D printers, sometimes if we don't have proper supports, or because of different laser powers and scan speeds, if there is any deformation or if there is any failure in the printed part, so again to reprint the same part, again we need to spend 3 weeks time, and here we will be spending lot of human resource, and the powder also will be using to print the part. So it will be a very lengthy process, and it will be consuming lot of resource as well. So to avoid that kind of issues, we have Ansys additive solutions where we can completely solve whatever the printing that we are going to do by using the machine. So the same procedure we can print by using this Ansys additive solutions, and we can check here itself what are the different issues or failures that will happen if we go for that kind of parameters, and we can change the parameters, and we can optimize the process by going with the additive solution. So in case if we perform any analysis like by using the mechanical or LS Dyna, so sometimes the product will perform well for that kind of for that loading conditions. But over the period of time, like let's say I applied a load of some 1,000 newtons on one particular geometry. So for that 1,000 Newton load, that particular product will perform well. But if I repeatedly apply that 1,000 Newton load for some 50,000 times or 10,000 times or 1 lakh times, so gradually the product will fail by creating a crack, or so some failure will be happen after a period of time. So that kind of fatigue analysis, if you want to perform, so we will be using the encode design life, or even Ansys mechanical will also like this solver also we will be using to solve that kind of fatigue analysis. Okay, and so Autodyne is also a solver just like LS Dyna, where we will be performing severe loading conditions like impact, blast, explosion. So this kind of problems we will be solving by using Autodyne. But majorly mechanical and LS Dyna will address 90% of our structural challenges related to different strength analysis, vibrations, fatigue, okay, thermal analysis, and drop test, impact, ballistics. So this all simulations can be done by using mechanical and LS Dyna, and these are specific applications. If someone is working on the, let's say, sheet metal operations, so this Ansys forming will be useful. And if someone is working on the multi-body dynamics, even the multi-body dynamics can be done in mechanical. And for the advanced contacts and advanced multi-body dynamic analysis, we will go with the Ansys motion. And Sherlock is specially designed for PCBs or electronic components to check the reliability of that particular components. And Ansys additive solutions is basically for the metal 3D printers. And encode design life is for advanced fatigue analysis. For normal materials, if you are using any structural steel, aluminum, copper, okay, if you are using this kind of materials, and if you want to perform the fatigue analysis, that will be done by using Ansys mechanical. And sometimes we will be working on composite materials like okay, or different duty cycles if we are having. So that advanced fatigue analysis will be done by using encode design life. So these are the different products that we have, different tools that we have in Ansys structures. And so for different kind of applications, we'll be using different tools, but most of our problems can be solved by using mechanical and LS Dyna. Okay. So similarly, in case if we have any electronic components, and if you want to perform the simulations related to the electronics, like we have the HFSS tool, where we will be using to solve the problems related to the antennas, 5G, 6G, okay, where you want to analyze, like signal integrity. So this kind of problems will be for this antenna design or 6G, 5G, for this kind of technologies if you want to work on. So we'll be using this HFSS. And similarly, we have the Maxwell, which is a low frequency electromagnetic simulation tool. So in case if you are designing any motors, transformers, if you want to see the electromagnetic fields or the heat generation or how much torque it will generate for a particular input and output voltage. So this kind of all problems will be addressed by using Maxwell. And similarly, if you are working on the PCBs, and in the PCBs or packages or any electronic components, if you want to see the power and signal integrity with respect to different heat generations, so this kind of simulations will be done by SI wave. And so IcePack is also a fluid simulation software where we will be using to analyze the thermal behavior. Suppose if we have if we consider our laptop, so in our laptops we will be having different electronic components inside the PCB, and when we perform any heavy tasks, so automatically the fans will be operated because of the heat generation when we are performing the heavy tasks. So if you want to see how this fluid flow when these fans will operate automatically in our laptop, so how the heat distribution in our PCB will get down, like how the thermal temperatures across our components will be cooled down because of the fluid flow inside the laptop. So this kind of simulations related to the electronic cooling we will be using the ice pack. Okay. And so similarly for the parasitic RLCG extractor for this kind of simulations we will be using this Q3D extractor. And in case if you are working on any motors, and if you want to perform the motor design analysis in a 2D, so we'll be going with the MotorCAD. And again, as we discussed, Sherlock is a electronics reliability software for any mechanical related external loading conditions if you have. So we will be using this solver. And for electromagnetic modeling and simulations, especially for the cables, we will be using the CMA 3D cable. So to evaluate the cable harness. So these are the four fundamental electronic products that we have for physics. So HFSS is majorly useful for the designing the antennas, 5G or radio frequency RF microwave components in order to perform EMI EMC analysis. So this HFSS will be useful for this kind of applications. And so similarly, SI wave is specially designed for PCBs or packages to analyze the EMI EMC analysis or power and signal integrity for the PCBs and packages. Okay. And so we have the ice pack, like we discussed. In case if you have any electronic components, and if you want to see the thermal behavior of these electronic components when a fluid flow is flowing across the components, so like that. Okay, and as we discussed, Maxwell is a tool designed for electromagnetic field solver. So in order to design any electric machines or transformers, actuators, or any other electromechanical equipment if you are designing, so this Maxwell will be useful to design those particular equipment. Okay, so like that, by using the Ansys technology, we can solve the problems, ranging from kilometers to nanometers. So if you are working on any technology or any physics, that might be any structures, fluids, or even the electronic components. So we can solve all these kind of problems, ranging from kilometers to nanometers, like photonic and silicon elements, which are in nanometers, for designing the antennas, which will be or 5G kind of technologies, which will be ranging from kilometers. Yeah. So like that, the simulation will help us to meet product code regulations. So whatever the product that we'll be working on. Okay. So whatever the product that we'll be working on, whether it is a drone or whether it is a any aircraft. Okay. So for each and every product, there will be some product code regulations where we need to meet that regulations, like by maintaining the strength or EMI EMC compliance, or so like that. The simulation will help us to meet that all product code regulations without directly jumping into the prototype or working on the physical equipment. Okay. And overall, it will improve our product performance and reliability. And we will also get to know what will be the root cause failure for our product. Okay. And so it will help us to reduce our product development time and cost as well. So yeah. So like that, we can simulate the problems of a simple components like shaft, gear, or to design the complete, satellites, and even the launching the satellites to create, like developing the rockets, so simulating the complete workflow from each and every component. So these are some of the companies who are using ANSYS software to launch the rockets, and to make sure the deployment of the satellites into the orbit, so that it will not collide with the other satellites. Okay. So each and every year, the usage of simulation software across all industries are going up, and so they are like. So these are some high-profile program success where they have used the ANSYS tools. So this is Lunar Orbiter mission where they have used the ANSYS electronics and STK and OTDK to design the electronic components in the satellites, and to launch the rocket, and to maintain the orbit of the satellites and rockets. Okay. So similarly, even to design and development of a James Webb Space Telescope, also they have used the ANSYS solver. Yeah, so this is another success story that we have related to the double asteroid redirection test, where they have used the ANSYS SDK to predict the path of the rocket and asteroids. Okay. So now I will showcase one simple demo in the presentation. So in case if you are working on any product, so at the initial level, and if you want to design, and if you want to see the results in a single window, like in a live, in kind of, once you apply the loads and boundary conditions to your product, and if you want to evaluate different results there itself by modifying the geometry, so we will be using the Ansys discovery. So in this case, I'm showcasing one discovery live demo related to the fluid simulation. Okay. So suppose these are the different structures we have. So in case if there is any fluid flow from one direction to another direction, suppose from this direction to this direction, if the fluid flow is flowing, and whenever these obstacles are there, so we can see how the fluid flow, where the turbulence is happening, and how much pressure that is acting on these particles when the fluid is flowing from this direction to that direction. So like that kind of simulations we can perform in the discovery. And in case if you want to do any modifications in a single window, like if you want to move these components from one position to another position, and if you want to see what will be the variation in the results if you do any modifications in the geometry. Okay. So like that, we can do everything in a single window by using the discovery for the initial simulation. Okay. So yeah. So here we can see, in case if you change the position of. So here we are seeing the results at different, like in different planes and in different directions. So how the fluid flow will be acting on these components. Okay. And in case if you want to do any design changes, so, let's suppose if you want to change, the position of this particular component towards this side. So there is no need to solve again. Automatically, the results will be updated as per the changes in the geometry. Okay. So like that, in case if you do any modifications in your geometry, the results will be automatically updated. So you can see if we change the direction or angle of this particular building, so automatically the fluid flow around that particular component or around that surroundings, the fluid flow will be automatically updated as per the geometry changes. Okay. So yeah, so like that, we can use the discovery tool for the initial live simulation where you can apply the loads and boundary conditions. And once we got the results, as per our interest, we can change, the position of different components, or the dimensions of the different geometries we can change. And as per our changes, the live, like it will show the live results. within 1 minute itself, it will give the results as per that. So yeah, so before we move into the complete workflow of mechanical simulation, I would like to showcase a few more things. Okay. So now, as we know that even if you want to solve any problem related to the electrical, mechanical, and fluids, so we can solve by using this technology. It was there. This technology was there from the last 30 to 50 years. Okay. So now we are stepping into the next generation as we are more into the artificial intelligence. Even the ANSYS also have few tools related to the artificial intelligence. Okay. So ANSYS AI Plus, where this ANSYS AI Plus will be useful to integrate any coding like but if you are well aware of the Python, so we can use the Python language to develop a product, whether it is a geometry creation or to do the complete workflow to extract any results. So you can integrate the Python. You can integrate the Python language with any of the solver and you can solve the problem. And so another solver that we have is ANSYS SimAI. So basically, to simulate a problem, so based upon the complexity of the geometry, it will take a few minutes to few hours or few days. Okay. So instead of solving the problem by using the real mathematical equations, even you can train your model by using the SimAI. And once you upload the new geometry, without going into much physics, automatically the artificial intelligence will predict the results and it will give you within few seconds. So that is SimAI. I will showcase in the next slide how the SimAI will be giving the results as per the kind of result we will be getting as per the inputs that we will be providing. Okay. So suppose if you are working on ANSYS and in case if you want to, if you want some guidance related to the workflow or if you have any queries or if you have any others, okay, or if you want to see the tutorials to the same kind of, components that you are working on. So for that kind of components, just like ChatGPT, we have ANSYS GPT, which is a virtual assistance to all different products. So by using the Ansys GPT, we can interact and we can give the prompts which are related to our work. And based upon the inputs that we will be providing, automatically it will suggest the workflow or the related content and all the reference links will be provided by using the Ansys GPT. So just like we use the Chat GPT, we'll be using it. But this Ansys GPT is available within the mechanical window where we will be solving the problems. Okay. So in case if you want to integrate your simulation results with the real world physical results, where you will be having where you will be taking the data by using the sensors of the physical system. So like that, you can create a twin of your simulation, and you can integrate the simulation with the real data which we generally taken by using the sensors, and we can create a twin by using the digital twin. Okay, so this is how the SimAI will work. Suppose we are working on the simulations of aerodynamics of these vehicles. So in case if we have 4 or 5 results, if you upload the all 4 or 5 results into the SimAI, so it will train the model and it will create an AI model. Suppose once the AI is trained, in case if you upload a new geometry, so suppose if this is the new geometry, so by considering the results of the previous models, it will automatically give the results for your new model. So there is no need to perform the simulation. If we have the previous data, based upon the previous data, we can train our model and we can upload the new design, and based upon the new design, automatically it will give all the results, whether it is the pressure that is acting on the outside, or how the fluid flow will be, where we will be having the maximum pressure or maximum velocity, turbulence. So all these kind of results we will be getting in a fraction of a second once we upload the new design. So like that, even we can use the SimAI for multiple designs. Okay. So this is a little introduction about ANSYS, and now we'll move to the demo. So Yeah, so let's solve one problem. I will showcase in the software completely. Okay, so I will showcase two different geometries. One is a single component and another one is a complete assembly. Suppose if you are designing this simple hook, okay, and if our objective is to redesign this geometry when this particular hook is subjected to 6 kilonewton. Suppose here we are using some fixed support or tangential support if we are applying here, and this hook is subjected to some 6 kilonewton in this area. So if you apply a 6 kilonewton load on this particular area, so initially we will be getting some stress results. Okay. So based upon this initial design, if you want to simulate, if you want to apply the fixed support or tangential or cylindrical support, and if you want to apply 6,000 Newton load here, and if you want to analyze where we will be having the maximum stress and where we will be having the maximum deformation, so like that kind of simulation, we'll see how we can perform. And in case if you want to step into the optimization, so instead of this original design, if you have a criteria like, so I want to minimize the mass. So if this original geometry is having some 500 grams or 600 grams, so instead of 600 grams, I want to reduce the mass. I want to optimize the geometry by making a lightweight, and also that lightweight geometry should not exceed 300 megapascal. So the maximum stress that is allowed in my geometry is like some 300 megapascal. So like that kind of constraints we can set, and we can even perform the optimization. Okay. So suppose so this is our original geometry where we will be having different dimensions for different sections, where we have the outer diameter, okay, connecting connection length, upper angle, upper bend radius. So like that, we thickness, fillet radius, lower radius. So we have different dimensions for this particular geometry at different locations. Okay, so these are the loading conditions that we are going to apply. So we are going to apply cylindrical support, and we will apply a load of 6 kilonewton in the downward direction by considering the element size of 1 mm. So let's see initially if we have this geometry, how we are going to apply this loading conditions and how we will be getting the results. And once it is done, in case if you want to go for the optimization, how we are going to do the optimization, we will see in this demo. So whatever the simulation that we will be performing, whether it is a structural or whether it is a fluid simulation, so all the simulations will be done by using a single platform called Workbench. Okay, so Workbench is a platform where we will be performing all different kind of simulations. Okay, so this is the Workbench window where suppose you want to perform any analysis, so that all analysis will be available here. So suppose you have a problem which is related to the static analysis where there is no time dependency. So we will be performing the static structural analysis, or if you want to perform any vibration analysis, okay, that might be the vibration might be because of some motors or IC engines, or even okay, so even wind loads or seismic loading conditions, so like that. Okay, so for that kind of vibrations, we will go with the harmonic response, random vibrations, response spectrum. Okay, so whatever the type of analysis, whatever the type of simulation that we want to perform, so that all kind of analysis systems will be available on this left side. So we will be going through that particular analysis system based upon our requirement. Okay. Okay. So like that, in case if you want to perform any multi-body dynamics, like if you want to see the complete mechanism, so we will be using the Ansys motion or rigid body dynamics. Okay. Or for the blast, explosion, bullet impact, car crash. So for this all kind of simulations, we will be using the LS Dyna. So whatever the structural simulation that you want to perform, whether it is a static or vibrations or impact, drop, so whatever the multi-body dynamics, whatever the simulation that we want to perform in Ansys, we can directly take the analysis system. So for each and every analysis, there will be total 7 steps. So whether you perform the static analysis or vibration analysis, so we will be having total 7 steps. So here we can see 7 steps. So the first step is choosing the analysis system. Based upon our project, what kind of simulation or what kind of analysis system will be suitable. So choosing the analysis system is the first step. And second step is adding the engineering data. So I will just delete all this remaining rows to avoid the confusion. Okay. So the second step is adding the material information. So if you have a single geometry or even if you have a assembly where we will be having multiple components. So for that all kind of assemblies or components, we need to have the material properties. Suppose if we have an assembly where we have 3 components, and if one component is made up of aluminum and another component is made up of structural steel, and if other component is made up of stainless steel. So we need to add all that materials in the engineering data section. So if we double click on the engineering data section, and here we can go to the libraries. Suppose if I go to general materials. So here I have different materials. Suppose I want aluminum alloy. So I will add the aluminum alloy. I want stainless steel. I will just click on this plus symbol, and I want structural steel. So like that, whatever the materials that we require, so we can add all the materials here. Okay, so I have added three different materials: aluminum alloy, stainless steel, structural steel. Okay, so these are the 3 different materials I have added. If you click on any one of the material, so here we will be getting the material properties of that particular domain. Okay, so like that, in the second step, we will add the material information, and in the third step, we will be creating the geometry. So we have, just like I showed in the presentation, we have the discovery tool to create the geometry, or even you can use the spaceline to create the geometry. So in case if you already have the geometry, we can directly import that. So, okay, so I'm importing this particular geometry. So like that, we can add the material information, we can import the geometry, and once we import, we can open the model, and we can apply the loads and boundary conditions, and we can solve the problem. Okay, so in this particular case, we have the original design, and for this design, we are applying the cylindrical support here, and we are applying a 6 kilonewton load in the downward direction. So okay, so this is the geometry that I have imported. Okay, so like this is the complete this is workflow, or the tree that we have to complete the simulation. So the previous 3 steps that we are already completed. So one is selecting the analysis system, adding the materials, creating the geometry. So these 3 steps are done here, and the fourth step, model, setup, solution, and results. So these all 4 steps will be done by using this GUI. Okay. So first, let's complete the model. So in the model, we will be doing a few things. Like suppose this is my geometry, and so you can see this is, once I click on my geometry, here I will get the information about my geometry. So these are the details of the geometry that I have imported. Okay, so by default, it is considering as a structural steel. In case if you want to change the material from structural steel to another material, like you can click on this button and you can select. So whether I want to apply stainless steel or aluminum alloy, so like that, whatever the materials that we want to apply for this geometry, so we can apply that. And so in case if you want to see the properties, what is the volume of this geometry, or mass, or centroids, moment of inertia. So like that, all information related to this geometry will be available in these details. Okay. So now let's generate the mesh. So the meshing is nothing but dividing a single geometry into multiple elements or small elements. So here I am discretizing this complete geometry into small elements with an element size of 1 mm. Okay, so this is the geometry that we are considering, and we have created a mesh with an element size of 1 mm. And now let's apply the loads and boundary conditions. Okay, suppose this particular phase I'm selecting. So here I'm basically here in structures we will be having different kind of loads and boundary conditions. So we can apply the acceleration, standard earth gravity, rotational velocity, rotational accelerations, pressure, okay, force, moment, torque, or bearing loads, bolt pretensions, line pressure, thermal conditions. So these are the different loads and boundary conditions like fixed support, displacement, remote displacement, frictionless support. So based upon our applications, we can use. Okay. So in this case, I am using cylindrical support. Okay, so I'm applying the cylindrical support. So this cylindrical support will be applicable to all the cylindrical phases. So here I have selected this phase and I have applied the cylindrical support. So in the cylindrical support, we have three constraints. One is radial, axial, and tangential. So for this particular phases that we have selected, if you want to make any one of these as a fixed or free, we can select like this. So if you want to make radial as a free or axial as a free or fixed, so like that we can apply the condition. So here I have used the cylindrical support and I have applied this condition. And so on this particular phase, we will apply the loading like as per our problem statement. So we have applied the cylindrical support here and we are applying a 6000 Newton load in the downward direction. Okay. So I selected this particular phase and I will right click on static structural and insert force. Okay, so I'm applying the force on this phase now. So we can apply the force in two ways. One is by using the vector form and another one is components. So vector is nothing but magnitude and direction. So we need to give the value and we need to select the direction in which direction that load is acting. And another way is components. Okay, so basically the components is nothing but in which based upon the global coordinate system. So here we can see based upon this coordinate system, we can apply the load. So I want to apply in this direction, which is negative y. So I'm applying minus 6000 Newton load. Okay, so like that minus 6000 Newton load I have applied here in this direction. So these are the loading conditions that we have provided. So cylindrical support here, and we applied a 6000 Newton load here, and we can insert the results as well. So suppose I want to see the deformation. Okay, and similarly, I will right click on the solution and insert stress results. So these are the different stresses that we can take out. And similarly, the strain values. And let's solve the problem. So this is our original design, and for our original design, we applied the cylindrical support and force, and we are checking the results. Okay, so once we got the results, we will see how we can. Okay, how we can optimize the geometry. Okay, it will. Yeah, it is solved. Okay, so now the solution is solved. If you click on total deformation, let me adjust the view. Okay, so if we click on total deformation, so here we can see we are getting the total deformation of 0.88 mm. So 0.8 mm is the maximum deformation, and this is the location where we got the maximum deformation. Okay, so for this 6 kilonewton load, we are getting a maximum deformation of 0.88 mm. And similarly, if I click on equivalent stress, okay, so here I have the stress. So this is the area where we are getting the maximum stress, and the maximum stress value is 270 megapascal. Okay, so here the blue color indicates less value and red color indicates high value. So here we can see in this particular region. So once we apply 6 kilonewton load here, we are getting the maximum stress of 270 megapascal load, 270 megapascal stress we are getting here. Okay. And so you can see that So in this area we are getting, so you can see here we are getting 270 megapascal, and here we are getting 40 megapascal stress, and here we have around 170 megapascal. Here we have very less 7 megapascal. Okay, we can see here. So like that we can check the stress values at different locations. So like this. So like in this way we can basically, okay, so we can add the engineering materials, geometry, model. Okay, so we can create the, like, we can insert the material, we can create the mesh, we can apply the loading conditions, and we can see the results. So for structural steel, we got 270 megapascal. In case if I replace the structural steel with stainless steel, okay, let's see the results. Okay, so you can see 1.93 into 10 to the power of 5 megapascal is the Young's modulus for the stainless steel, and for structural steel it is 2. Okay, so now you can see earlier we are getting 0.8 mm is the maximum deformation for the structural steel, and for the stainless steel we have 0.91, and the equivalent stress is almost similar. So we are getting 270 megapascal is the maximum stress, but the deformation is changed to 0.91 instead of 0.88. Okay, so now the maximum stress that I got is 270 megapascal, but the maximum allowable stress in my geometry is 300 megapascal. So by giving the constraint, so 300 megapascal is the maximum maximum stress that is allowed. But by taking this constraint, if I can change the shape of my geometry, or if I want to reduce the mass of my geometry, how we are going to reduce, we will be seeing that now. Okay. So basically here we will be having two type of, yeah, so this is our geometry, initial geometry. So once we solve the problem, we got 270 megapascal is the maximum stress, and our original mass of the geometry is 110, like 1100 grams is the original weight, and opening width. So this is the opening width. So opening width of this geometry is 64 mm. Okay, so this is our original design, and yeah. So here basically we will be having two type of parameters. One is input parameters, and another one is output parameters. Okay. So here we can see. Okay. So if you just a second. Okay. So here we can see these are the output, these are the different properties of the geometry, dimensions of the geometry. So outer diameter, connecting length. So these are the different properties. So these all are the input parameters. So geometry properties are the input material or input parameters. Or if you select any material, whatever the properties that we are considering, Young's modulus, Poisson's ratio. So these are input parameters. And so similarly, we will be having the output parameters as well. Like total deformation is the output parameter, and equivalent stress is the output parameter, and mass is the output parameter. So whatever the things that we will be providing, to the system as an input to solve the problem. So these all things will be considered as the input parameters. And once it will solve the problem, whatever the outputs that we will be getting, so these all things will be output parameters. Okay. So let's say I am considering, so I click on the force. You can see this X component, Y component, and Z component. So these are the input parameters. So the force is the input parameters. So if I click on any one of these empty box, this input parameter will be created in the workbench. Okay. So I consider this Y component minus 6000 as an input parameter. And so if I go to the mass, so I just click on this mass parameter P. So wherever we click on this empty box, that particular thing will be considered as a parameter. So dimensions are input parameters. So based upon the dimensions and based upon the material, mass is the output parameter. Okay. So similarly, equivalent stress maximum is the output parameter. Okay, so whenever we click on this empty box, automatically the parameters will be created here. Okay, once I double click on the parameters, so here we can see we have two type of parameters. One is input parameters and another one is output parameters. So input parameters are dimensions of the geometry. So these are the different dimensions of the geometry. So these are the input parameters. And force is also an input parameter. Okay, and the output parameters are, you can see mass. Mass is the output and equivalent stress is the output. So like that, we can take anything as an input or output parameters. Like here, I am considering total deformation as the output, or one of the parameter. Okay, or the maximum strain that we got is 0.0014. So this one also we can consider as an output parameter. So like this, we can, whatever the things that we want as an input or output parameters, all the things will be added here. Okay, so now these are the dimensions. Okay, these are, see, you can see thickness 20 mm is a dimension, depth, lower radius, ds angle, length, diameter. So these are the input parameters we have. So these are the dimensions of our geometry. Okay, you can see outer diameter. Okay, so here we have radius, force, thickness. Yeah. So the diameter 32 mm here we have, so for transition radius. So that all dimensions we have here. So in case this is the original geometry dimensions. In case if you want to try with different dimensions, and for these different dimensions, what will be the results? So for these dimensions, we have this mass, and for the stainless steel, we have this mass. If you go with the structural steel, it will get 1100. Okay. So equivalent stress 270 megapascal for these dimensions. In case if I change the dimensions, what will be the solid mass, stress, deformation? So like that, we can in this in this particular window itself, we can give the different values and we can run the problem. So based upon the inputs, automatically it will give output values. So this is one way. And another way is to perform the optimization by using the OptiSlang. Okay. So in the OptiSlang, we have three different stages. First one is sensitivity analysis. Suppose if I drag and drop the sensitivity analysis here. Okay, so once I link the sensitivity to the static analysis, a new window will pop up. Okay, so it is loading. Yeah, so you can see these are the input parameters that we have. So we have constant values 23, okay, 20. So these are the dimensions. So in case if I want to give a range, so the output diameter I want in between 28 to 35 mm. For the connecting length, I want 20 to 50 mm, and opening angle, I want 10 to 30 degrees. So these are the ranges I want. In this range, I want one design. Okay, so these are the ranges. And in this range, I want a design, optimized design, which will satisfy my results. So like that, initially we can give the results here, like the ranges. So suppose thickness P1 20 mm is a, initial dimension, but instead of 20, I will go with 15 to 25. So I want the range from 15 to 25. Okay. So similarly, the fillet radius. So fillet radius, we have 2 to 4 mm. I will take. So it has 3 mm. So in the initial geometry, it has 3 mm. And instead of 3 mm, I want to check. I want a design in between 2 mm to 3 mm. Okay. So like that, we can give a range. We can give a range for all the dimensions. So whatever the dimensions or whatever the input parameters that we have. So even the load as well. So 6000 is the input that we have provided. If you want to test in between minus 6.6 kilonewtons to minus 5.4 kilonewtons. So like that, you can give a range. Okay, so you can provide the range like this. For each and every dimension, you can give a range. So I will go with this other things automatically. And okay, so you can see these are the ranges that we have provided, and these are the output parameters. Okay, So my objective is to minimize the mass. So I want less mass. So I will just take, I will keep a constraint. So I just selected one objective. Okay. So my objective is to minimize the mass. So I will take this solid mass here. Okay. So my objective is to minimize the mass. So the criteria is minimum. So means my objective is to reduce the mass. Okay. And I will give one constraint. So my constraint is equivalent stress. So I am taking the equivalent stress maximum. Okay. So I have 270 megapascal as a maximum stress. So my constraint is, so the equivalent stress should be less than or equal to 300. Okay. So whenever, if I try, so I gave different range of dimensions. So if it will create some 100 samples, so my criteria is out of that 100 samples, I want to select a geometry which is having as minimum as possible. The mass should be as minimum as possible, and the stress should be less than or equal to 300 megapascal. So these are the two conditions that I have provided. So I give a range of dimensions, and okay, so in that range of dimensions, I want to select a geometry which is having minimum mass, and the equivalent stress should be less than or equal to 300 megapascal. So like that, I can provide the conditions, like I can give any variables. So this is my objective, and I have provided one constraint. Even you can set a limits as well, limit stage, like the deformation should be 0. It should be in between 0.02 to 0.024. So like that, you can give a limit or constraints. So like that, you can provide, and I'm going with. Okay, so these are the different sampling methods. So we have provided the ranges, like these are the different ranges. So in between, like in these ranges, how we are going to select 50 samples or 100 samples or 1,500 samples will be depend upon these mathematical models. So full factorial method or advanced Latin hypercubic sampling method. So these are the different sampling methods we have. So you can select any one of the sampling method and you can finish. Okay. Okay. So like that, you can create this condition. So here by default, it is taking 300 samples. So in case if you want to go with more number of samples like 1,000, okay, if you give more number of samples, it will take more time, or 30 samples or 20 samples. So like that, you can take a few samples here, or if you want to change so you can see the complete workflow. So these are the dimensions and these are the ranges. And so this is our criteria. In case if you want to edit before you solve, you can select this. And these are the number of samples you want. And these are the MOP, so input and output parameters. And the other settings like result designs once we got the results. So all these things will be there. So once it is done, you can right click and update. So it will optimize and it will solve and it will give the sensitivity results. So it will take some 20 to 30 minutes to solve this problem. Okay. So, but I will showcase the solved problem now. Okay, so I already solved this, and even I integrated this sensitivity analysis to the optimization as well. Okay, like we have here sensitivity and optimization. So this is optimization, and this is robustness. Okay, so these are the results. So here I can see I have total 30 different samples. Okay, so I have 30 different samples, and so these are the sensitivity of that different inputs to the outputs. Okay, so you can see equivalent stress. If I change the thickness, the sensitivity is more, but the depth is very less sensitive to the equivalent stress, and lower radius is very less sensitive, and these all other things are not affecting the equivalent stress. Even if you change these dimensions also, your equivalent stress will not change. Okay, so there is some impact on force. So force will also change the equivalent stress, and the mass. So this is mass. Okay, so how the mass will be affected if you change any one of these dimensions. So the mass will be more into like depth. Okay, so and so these are the opening width is one of the parameters, and slipping height is other parameter that we have considered. Okay. So like this, it will give the results. So you can see opening angle versus lower radius, and this is slipping angle. So these are the different result points that we have. Okay. So here it is showing the best design is 18. So you can see select best design, design 18. So out of 30, it is showing by default design it is best design. If I go back to the parameters, okay, so here you can see initially I have only one set of results. Okay, so this is design point 0. These are our original dimensions. So these are our original dimensions, and these are the results of the original dimensions. But you can see in the bottom, these are the different designs that we have considered. If you give 300, it will give 300 different design points. And for all these 200, 300 or 1000, it will showcase the results. Okay, you can see the different like, yeah. So you can see the equivalent stress 270, 254, 200, 316. Okay, so like the 240, 258. So these are the different equivalent stress results for different designs. Okay, these are the slipping height, opening angle, mass. So like that, we can generate hundreds of samples, and we can see the results for all the 100 samples. And even the system, like the solution will automatically suggest you which is the best design out of these 100 samples. Okay. So if you want to see that best design, if you want to if you want to see the results in the in this window itself, if you want to see the best design, okay, so we can go back and so suppose the best design is suppose 18 is the best design. Okay, so you can select that and you can set it as a current. Okay, so once you set it as a current, these results will be shown in the graphics. So like that, you can perform the optimization and you can select the best design, and the best design you can open is optimizing. Yeah, so okay. So the updated design, instead of original geometry, the updated design we are opening now in the static structure. Okay, so these are the dimensions. Okay, so this is the updated design that we have. It is having the same 270 megapascal, but if you see here, it is having 1.06 as a weight, because in this case I have considered only 20 samples. Okay, so in this 20 samples, you can see 1.066 is the mass of this current one that we are seeing. The original one is near to 1100 grams, but this one, this much, like the current design that we are seeing is 1.06. So even we have the lower one as well. So 960 grams geometry is also there, which is having 277 megapascal. Okay. So like that, we can generate different designs, and we can select the best design. So this is one of the optimized design we got for this model, 708 grams. So the original one is 1100, and this optimized one is uh, 708 grams out of 300 samples. Earlier I run with 300 samples, and in the 300 samples I got this 708 is the optimized one with the maximum allowable stress of 265 megapascal with opening width of 51.31 mm. So like that we can create the optimized design. Okay. So even if you want to solve the complete assembly, this is the complete assembly. So basically this is a glow ball where the fluid will be interacting. Okay, so where the fluid will be interacting with this all surfaces. So these are the surfaces that will be exposed to the fluid pressure. Okay. So in this particular assembly, we are like basically this glow ball will be connected to the pipes. So this glow bulb is connected to the pipe on this surface and on this surface. And these are the surfaces that will be exposed to the fluid, and it is subjected to a pressure of 7 megapascal. Okay. So in this case, also like in case if you want to, you know, in case if you want to, because in the previous simulation I have showcased only a single component. If you want to consider the complete assembly also, you can consider. And in between the components, we need to create the contacts. So bonded means completely fixed or frictional contacts. So like that kind of contacts between the geometries we can define. And even in case if we have any bolt and nuts, so we can consider the bolt and nuts in the form of different things. So this is a complete bolt and nut. So instead of bolt and nut, you can create a 1D beam to represent the bolt and nut, or you can consider cylindrical, circular, cylindrical kind of components as a connection between bottom surface and top surface. Okay. So like that, you can apply the pressure. So here I have applied a pressure of 7 megapascal here, and the frictionless supports. Because the frictionless supports we are using here because this is the connection between this geometry to the pipe. Okay. So the frictionless support or the holes. So like that, we can apply the conditions, and even in case if we want to consider the bolt pretension, because whenever we tight the bolt, some bolt pretension will be there inside the bolt. So that bolt pretension we also will be considering, and we will be checking the different results, like where we have the maximum stress. So you can see, so this in the bolt and nuts we are getting the maximum stress. Okay, so normal stress in any particular surface. If you want to see the results in any surface. Okay. So like that, we can check the results for a single geometry or a complete assembly for different kind of loading conditions like static analysis, dynamic analysis, and we can take the parameters and we can optimize the geometry. So like that, we can do different kind of innovations, and we can improve the design of our structure, and we will be make sure the stresses, the deformations, the strength of the geometries that we have, whether it is assembly or the full geometry that we can analyze, and we can optimize the geometry and we can improve the design. So yeah, so this is from structures. So in case if you have any doubts or if you want to discuss anything, you can post your doubt in the chat box. Okay, before we jump to the fluid analysis demo. So I hope you understand. Generally, in case if you want to work on any structures, how we will be applying the loads and boundary conditions, how we will be taking the results, and in case if you want to optimize your design, how we will be giving the range of dimensions, and out of that, we will be selecting the samples, and from that samples, we will be selecting the best sample, and we will optimize the geometry. Okay. So yeah. In case if you have any doubts or if you want to discuss something, you can put it in the chat box, your query. Okay, so yeah, so let's move to the fluid section. And so in future also, if you have any doubt or if you want any support, so you can reach out to us. I'm dropping my mail ID in the chat box. So this is my mail ID in case if you want to discuss or if you want to uh, ask anything or if you need any support. So you can reach out to my mail ID, anything related to the structure. And now we will move to the fluid analysis. We will see what are the different simulations that we can perform using the fluids. And yeah, so over to you, Ganesh.
Yeah, hi Ravi. Yeah, I will just share my screen. Okay. Yeah. Hi everyone. Myself Ganesh. So I am taking care of the CFD side actually. So the idea of this webinar will be to give an overview of Ansys actually. I hope he given the basic overview of Ansys and from the structural part. So now I'm going to cover regarding the CFD part actually. So we'll cover the whatever the capabilities in different aspects in the CFD side as well as the structural side. So maybe it depends upon application to application as well. So since you are interested in some particular application, you can please feel free to reach out to us. So we'll plan separate session, meeting, separate discussions. Actually, we can plan it. So now I'm just going to cover regarding the what are the capabilities will be there in the CFD side actually. Okay. Yeah. So basically, this is the overall Ansys product portfolio. So already Ravindra covered major parts actually. Okay, so right now I'm going to cover regarding the CFD part only. Okay, so in the similar manner, we are having a different bundles as well actually. Okay, so right now he covered the structures part. So similar manner, we have the capability in the electronic side as well as optical side, as well as if you're interested to perform a system level simulation, we have the capabilities. Okay, so if you're interested to explore in those area, we can please and sorry, you can mention your what are the product portfolios, and then you can reach out to the mail address whatever Ravindra shared. So we can happy to connect and then we can have a separate discussion also. Okay. So moving ahead, I'm going to cover regarding the CFD part. Okay. So basically, the CFD is kind of computational fluid dynamics to see the flow behavior, how the flow properties are varying, like pressure, temperature, and velocity, and in terms of how the heat transfer is taking place. Actually, whenever some kind of combustion is taking place, what will be the maximum temperature? How the heat is transferred from the in terms of conjugate heat transfer, how the heat is transferred from the fluid to the solid, and from the solid to the outer, like outer atmosphere. So, in terms of modeling the fluid properties to calculating the fluid properties at each and every locations and to calculate the heat transfer at each and every locations, and if there is some kind of two three species are coming and interacting, how the species behavior is happening. So in order to simulate and you have to see the scenarios, we'll use the CFD tools actually. Okay, and in terms of turbomachinery applications, so there are a lot of different aspects as well. So just to give an overall idea, so CFD will be used generally used to model the fluid flow behavior as well as the heat transfer related applications, and as in terms of multi-phase related phenomena actually. Okay, so these are the major aspects actually. So in coming into the application side, so CFD will be used either in a single phase flow or in terms of multi-phase flow. So single phase in the sense only one phase is coming, either only water or liquid is coming. Okay, how the behavior of the liquid will be there inside the ducting system or inside some kind of what is it, flow or an external bodies, that is flow over a aircraft or flow over a car, how we can able to design it. So those aspects will comes into picture. Multi-phase will comes into picture whenever the two or three phases interacting with each other. Whenever the evaporation is happening, some due to the heat exchangers during the operation, the oil will get evaporated sometimes due to severe heating. So how the evaporation is happening, so how the condensation is happening inside the headlight designs actually, fog formation will be there, right? How the condensation is forming actually. So in order to see the different phases, how the phase change is happening actually, how the oil is interacting with the air, or oil is interacting with the hot gases actually. So how the behavior is happening. So in order to model the different phases also, we can able to model in the Ansys actually. Okay. And similarly, in terms of heat transfer application, we can able to model the conduction as well as the convection as well as radiation heat transfer as well. Okay. And wherever the reactions is taking place, in terms of combustion application, wherever the aircraft propulsions will be there, right? So over there, how the combustion is taking place, and ICE engine combustion will be there. So how the maximum temperature is getting generated, how the maximum pressure is generated, how we can able to avoid, what is it, how we can able to maintain that within the safer limit. So those kind of detailed analysis we can able to perform using the CFD tools. And in terms of turbo machinery application, turbo machinery includes like design of the fan, compressors, pumps. So all these things will cover in the upcoming slides. I'm just giving an idea. And if you're going to optimize any of the shape, so for external aerodynamics, like external car design, so we have to design in such a way that the drag force should be as slow as possible. In the similar manner, in the aircraft also, we have to design in such a way that we have to reduce the drag forces and we have to improve the lift forces. So for that, how we can able to optimize the shape, that we can able to do actually. But that's for internal, means external flow. For internal flow, we have to reduce the shape in such a way that the pressure drop should be minimum. So like this, we can able to do the kind of shape optimization also. And we have the capability in terms of electronic cooling actually. Whatever you are using some kind of electronic applications, definitely we have to design the cooling systems actually. So how we can able to design the cooling system so that we can cover in the CFD part actually. And similar manner, Ansys, one of the beauty of Ansys will be it's a kind of multi-physics capability. It's not a what is it, design only for one physics, because whatever the major applications, whatever you are working on, whatever the um, like I'm just considering kind of recent trends like designing of the drones or designing of electric vehicles. So it is not only a kind of mechanical component only. So it is a combination of mechanical as well as electronic components. So all the physics will comes into picture, right? So transferring data means what is it? In order to perform this kind of multi-physics analysis, so ANSYS plays a major role actually. I'm taking a two cases example. First case is regarding the battery design actually. If you consider battery design, so the heat will keep on generating due to the working of the battery, right? So how the heat is getting generated, that we can simulate and see using the CFD tools, and we can couple with the mechanical, and then we see because of the heat getting generated, how the thermal stresses are getting generated, how the deformation is happening. So like this, we can couple with the mechanical and to see the like what is the fluid structure interaction analysis. It's not only on the battery. If you're considering the aircraft also, the flow will takes place across the, means what is it, over the wing and over the aircraft, right? So how the pressure variation will be there at each and every location of the aircraft wing, whether the wing can able to sustain the pressure load or not. So for that, first we have to perform the CFD simulation, and then we have to calculate the pressure at each and every locations using the CFD, and we have to transfer the data to mechanical, and that will act as a load, pressure load. So how the for the pressure load, how the deformation is happening. So like this, we can couple with the different physics actually. And similar manner, if you're performing some kind of electronics, suppose if you are designing some kind of motors, so generally using the electronics tools, we'll see how the motor winding designs will be there, and then we perform the simulation and we get to know what are the losses are getting generated. So that generally the losses means how the heat is getting generated, right? Losses is generally the heat. So once we perform the electronic simulation using Maxwell tool, we can couple with the mechanical or CFD to see how we can couple with the CFD to see how the heat dissipation is happening, and whether you have to keep some kind of fans or some kind of cooling systems to dissipate the heat in a much faster rate. So that in that way we have to couple with the CFD and we have to perform the simulation. If you want to see only the thermal stresses and deformation, then we can directly couple the electronics results with the mechanical to see how what will be the thermal stresses and what will be the deformation. So we can able to couple with the different physics. We are having a common platform called Workbench where we can able to integrate with the different physics actually. Okay. So I will just move into just showing some of the example cases so that you can able to easily interpret. So first thing will be regarding safety will be used in terms of internal flow simulation. The internal flow inside the cabin or internal flow inside any kind of piping systems. So how the flow is taking place, how the velocity and how the pressure variations are happening. Suppose if we change the vent location, how the flow is reaching each and every corner of the cabin actually. Okay, so this is for some kind of HVAC applications. Similarly, in terms of piping systems, we can able to see suppose some bend like U bend will be there in a sense. Definitely over there the pressure drop will be much higher. So how we can able to design in such a way that the pressure drop should be as minimum as possible. So in that way, we can able to design, and then we can able to check the whether the design is meeting your requirement, and accordingly we can able to redesign our system. So this was just an internal flow cases, and flow and external flow cases. How the car design should be there, or some kind of two wheeler, or some kind of outer shape. How we can able to optimize it so that we'll have a very lesser drag force actually. Okay. And similar manner in terms of combustion application, how the combustion when it is coming out of the nozzle, what will be the Mach number that is generating at the exit of the nozzle, whether we are reaching the supersonic condition or not, and how the nozzle flume is getting generated, what will be the maximum temperature that we are getting generated inside the flume actually. So how the flume formations will be there. So those kind of what is it, extensive simulations we can able to do, and we can able to simulate the scenarios actually. Okay. And in terms of turbo machinery, like designing of the fans, compressors, turbines, pumps, so all those designs we can able to do in terms of we can able to change the design of the blades such that we can able to see how the performance of the turbine has been improved, how the performance of the pump has been improved. So like this, we can able to play around the geometrical parameters as well as the input conditions what we are giving, so that we can able to keep on changing, and then we can see how the performance has been varied, and then we can come to a final means final design actually. Okay. And in terms of thermal analysis of the battery, so Ansys having the separate capability for simulating the battery for EV vehicles. Okay, so we can able to simulate how the maximum heat is getting generated inside the battery due to electrochemical reactions actually. So there are different models will be there to calculate the electrochemical reactions as well. Okay, and in terms of heat exchanger application, how the heat is getting transferred from the fluid to the solid and to the what I say to the other gaseous domain actually, how the heat transfer is taking place. It's a kind of conjugate heat transfer. Suppose if the fluid, whatever the fluid that is coming, that is transferring the phase, that also we can able to model and we can see actually. And in terms of fuel tank design actually, so whenever you're transporting the fuels actually, so the major things will be it will leads to some kind of like a sloshing effects actually. Whenever we are there is some sudden transient effects, so the sloshing will be much higher, so that may break the what to say, that may damage the fuel tank walls actually. In order to avoid the sloshing effects, we have to keep some kind of baffles, so that will restrict the sudden sloshing effects actually. Okay, so how we can able to design the baffles actually. So those kind of detailed simulations we can able to do. Okay. And in terms of, as I mentioned, in terms of single phase flow, we can able to see how the aerodynamic behavior will be there, and how the suppose if you are working on some kind of submarine applications, how the hydrodynamics behavior will be there. Like behavior in the sense how the drag force and how the lift force will be there, and how the moment generation is there. Okay, some sudden moment is getting generated or not. So uh, how the overall performance of the aircraft or submarines, that we can able to simulate and we can see. Okay. And in terms of internal flow inside any kind of manifold or any kind of piping systems, we can able to see how the flow patterns is happening, where the maximum pressure drop is happening actually. Okay. And in terms of valve application, so how by changing the valve angle, how the pressure variation is happening across the valve actually. Is there any some kind of sudden pressure jump is there or not? So like this, we can able to simulate and see. And if you are going to see at different angles, we can able to simulate and see. And if you want to see as a transient phenomena, it has to keep on moving. That also we can able to predict using the 6 simulations actually. Okay. And we can able to predict the noise also, because of that how much amount of noise is getting generated. That also we can able to uh, simulate using the CFD tools actually. Okay. And regarding the heat transfer point of view, we can able to see using the wherever the heat transfer applications will be there, we can see where the maximum hotspot is there. Okay, how we can able to avoid the maximum high temperature regions by using some kind of cooling system, how the cooling system design has to be there, and how we can able to improve the efficiency of the cooling system. So in order to optimize the cooling systems, so definitely we have to go for the CFD tools, and then we can able to see by changing the flow rate how the cooling efficiency has been improved actually. So like this, we can able to keep on iterating the design parameters, and then we can come to a desired output actually. Okay. So to see the overall thermal behavior in terms of conduction, convection, as well as radiation. And then in terms of conjugate heat transfer analysis also we can able to see. Okay, in terms of battery, generally due to electrochemical reactions, how the heat is getting generated, and due to flow of the current, how the heat is getting generated. That also we can able to model. And this is a case of conjugate heat transfer inside the piping systems actually. And this is a kind of case of heat transfer system or the antenna design. Actually, they will perform some kind of simulations in the electronics tools, and then we can couple with the CFD to see how the heat distributions will be there and how the heat dissipations will be there. Suppose if you are adding some material on the outer surfaces, how the heat dissipation has been improved. So like this, we can able to predict the scenarios actually. Okay. Yeah. So, and in terms of reacting flow applications, how the combustion is taking place, whether the whatever the combustion parameter that is given that is correct or not, whatever the expected behavior is reaching or not, in terms of temperatures and in terms of pressures, actually, whether it is within the desirable, what is this, within the safer limits or not. So, in terms of combustion applications, like in terms of spacecraft propulsion applications, and in terms of IC engine applications, how the spray is coming and how the spray impingement will be there, and impingement of the two sprays, how it is getting interacting with each other actually, and what will be the residence time of the spray, and how the particles are interacting. Okay, and in terms of like we are having a separate tool for only modeling the particles that I will cover in the upcoming session. We call Ansys Rocky. So that is only for modeling the particle level analysis actually. Okay, and here in reacting flows we can able to see how the combustion is taking place and what will be the maximum temperatures, and in terms of how the reactions of the two species are happening in terms of reaction rates actually. Okay, and how the density variations will be there. So all those property what is it in terms of flow property aspects, we will see how the density variations will be there and how the heat transfer is taking place surrounding to the regions actually. Okay, so uh, in terms of designing any kind of burners actually, so how we can able to improve the burners so that whatever the some kind of gases that we are delivering, that is sufficient enough to take the combustion as per our expectations. So like this we can able to redesign our combustion systems and then burner systems as well actually. Okay. And Ansys having the capability in the turbomachinery aspects in terms of designing the compressors and then pumps actually. Okay, and by changing the blade angles, how the discharge of the pump has been improved, and what will be the maximum pressure that you have achieved as an output actually. Okay, that we are getting, and what will be the maximum velocity that is coming out actually. And by changing the flow parameters, what will be the inlet condition that we are giving inside the pump actually. Okay, so in order to get the delivered output, so at least we should what is it we should keep the inlet conditions in such a way that so that we are getting the desired output. So in that way we can optimize our design input parameters and geometrical parameters to get the performance of the pump or performance of the like any kind of turbo machinery components like compressors and then turbochargers section. Okay, so it's having the capability in terms of designing any kind of water fluid as well as the air fluid, or in terms of like in terms of ships, propellers will be interacting with water, right? So how the interactions will be there, how the rotation of the propeller it is affecting the water in the wake region, that is behind the region, how it is affecting, how the flow physics are totally changing, that we can able to simulate, and we can actually see like how the flow behavior is there and how the velocity change will be there and how the pressure change will be there across the propellers actually. And in terms of multi-stage compressors, how the each stage affecting the behavior means successive stages actually, like in terms of pressure drop and in terms of what will be the velocity variations, that we can able to nicely predict it actually. And we are having the capability in terms of free surface flows. Free surface flows in the sense wherever the top surface of the fluid is open to atmosphere, like in terms of submarine means not a submarine, like in terms of designing a ship applications actually. Okay, the top surface of the water is open to atmosphere actually. Okay, designing any kind of ships, how the interaction of the water with the shape of the hulls will be there actually. Okay, whether some kind of pressure loading on the some kind of pressure like wave patterns we can specify in the water, and we can see because of the wave patterns how it is affecting the means from the CFD simulation we came to know what will be the pressure acting at each and every locations around the ship or around the hull actually, and then we can couple with the mechanical to see because of the pressure what will be the deformation is happening. So like this we can do a kind of multi-physics simulation as well. And as I previously mentioned, not to avoid the large slashing effects, we have to create a baffles actually, so that if you didn't keep any kind of baffles, so it will create a large slashing that will that will damage the walls of the fuel tank. So if we keep the baffles, so that slashing effect has been reduced in a much drastic way. And in terms of hydro turbine, like if you want to design a kind of hydro turbines, so that also we can able to simulate using the multi-phase flows, like interaction of water with the air, how it is behaving actually, that we can able to simulate and see actually. Okay, so those kind of detailed simulation involving multiphase we can able to perform, and we can able to predict the performance actually. Okay. And this is what I mentioned regarding the fluid structure interaction analysis. So we are having a common platform called Workbench. So as you can able to see in the left side, whatever the physics will be there. So whatever the let's say different things like mechanical, CFD, and electronics, all the physics will be there in the Workbench actually. Okay, so once you perform any kind of like in this case we are coupling with the CFD with the mechanical. So first we have to perform the CFD simulation. That is, we are having a flagship product called Fluent. So over there we perform the CFD simulation. Once the CFD simulation has been done, so the integration is happened in a very simplified way. So you just have to simply drag the results of the CFD and drop it to mechanical, so that the results automatically is getting uploaded into mechanical. So in mechanical, we have to specify wherever the what is there, some kind of fixed supports will be there. We have to specify the supporting systems, and then we can specify the load is directly transferred from the CFD actually. So if you specify those things, so automatically the software will calculate what will be the stresses and deformation due to the CFD load actually. Okay. So like this, the integration is a very is designed in such a simpler way. So just have to simply drag and drop into the another physics actually. Okay. So like this, we can able to first to perform the CFD simulation for the floor and aircraft and see what will be the pressure variations at each and every location, and then we can couple with mechanical and to see the because of the pressure load what will be the stresses and deformation. So suppose if you're performing some kind of combustion related application, so over there the major aspects will be in terms of temperature. So we have to perform first the CFD simulation to see what will be the temperature at each and every location due to the combustion, and that data we have to couple with mechanical, and we have to specify I'm transferring the pressure instead of right now in this case we are loading the pressure data. So in terms of combustion case, it is a temperature is a major concern. So we have to specify temperature I'm going to load on CFD. So that is the only specification you have to specify. Suppose if in some cases we have to include both pressure as well as the temperature, then we can specify pressure as well as the temperature. So the data automatically transfer from the CFD to mechanical actually, and then we can see what will be the stresses and deformation actually. Okay. And in similar manner, we can couple the different physics as well. As I previously mentioned, we can couple the electronics results with the CFD or electronic results with the mechanical as well. So next thing is regarding the battery thermal management. In battery thermal management aspects, generally right now the EV sector is booming actually. So most of the customers are working on the EV side as well. So I'm just having the separate model for battery to predict the electrochemistry behavior and what will be the heat is get like how much amount of heat is getting generated due to electrochemical reactions actually. That we can able to actually predict, and then we can able to see how the heat generation is happening with respect to time, and how we can able to suppose if some cell subjected to failure, whether the thermal propagation is happening to the nearby cells or not. We can call it as a thermal runaway. So whether the thermal runaway is happening to the nearby cells or not. If thermal runaway is happening, then how we can avoid it by using some kind of cooling system. So what kind of cooling systems we have to design it, and how we can able to improve the cooling system. So all those aspects will be covered in the using the CFD. And we can able to see we can able to see the impact of the temperature and C rating actually. Okay. uh, Team, actually, can you kindly confirm you can able to hear my voice clearly? No?
Yeah,
Either
Ganesh,
Ravi
it's
or
clear.
yeah. Okay, Ravi. Yeah, so we can able to see the how the impact of the temperatures and by different environmental conditions, definitely we have to model right, and how the battery is performing, that we have to see, right. So in that case, we have to keep on changing the environmental parameters. Like suppose if the environmental condition is 27 degrees Celsius at 45 degrees Celsius, how the battery is performing. To see the with respect to different environment, how the performance will be, that also we can able to simulate actually, and we can see how the effect of C rating will be. C rating is just the time, how much time it is taking. Suppose if you're increasing the I can say like if you're increasing the accelerator, it means we are throttling much at a higher speed, right? So in that way, like by different C rating, how the performance of the battery will be good actually. That also we can able to model in C. Okay. So we can able to model the prismatic cells as well as the cylindrical cells, and this is the case of the prismatic cells along with the cooling plate action. Okay, how the temperature variations will be there. So like this, we can able to have the separate models for battery to address all the battery thermal management, okay, in terms of battery thermal management aspects actually. Okay. And for a kind of rotating machinery designs, so we are having a complete system actually from what is it, from the 2D to 3D overall designs we can able to do it in the Ansys tools actually. Okay, so first thing, using the blade modeler we can able to design our blades actually. Okay, and once we have the blade design, and in 2D itself we can keep on changing the different parameters, because when it comes to blade there are a lot of variables will be there. So by changing each variables, how the performance has been improved. In 2D itself, we can, for our desired performance, how the blade designs, we have to keep it in 2D. First, we will perform a kind of 2D simulations. Once the 2D simulation has been done, that we call it as a pre-design. So we are having a Vista tools as well to perform 2D simulations. So once the 2D simulation has been done, we'll go with the 3D model. So we are having a different 3D tools as well, design modeler. Right now we are having a advanced tool called Spaceline, where we can create a 3D model. So once that is done, then we'll do the kind of meshing. That is a kind of process involved in the simulation process. Okay. So once the meshing has been done, next we have to perform the flow analysis, how the flow variations will be. That we'll see across the blade how the flow performance will be good. Uh, uh, at what location the pressure drop is maximum, how the flow separation is happening, whether the flow separation is happening or not, any kind of recirculation regions are there or not. That we can able to simulate using the flow analysis actually. So once the CFD simulation has been completed, that we can couple with mechanical, and then we can perform some kind of FSA simulation, that is fluid structure interaction analysis. Okay. And in the similar manner, if you want to perform the mechanical, like vibration analysis, we can perform it actually. Okay. And we can once the FSA simulation has been completed, if you want to see because of the rotation how much amount of noise is getting generated, kind of related to the acoustics will be because of two reasons actually. Because of the flow, if it is due to flow, that is we call it as air acoustics, that we can perform using the CFD tools. Suppose if it is due to some kind of vibrational effects, so we call it as a vibroacoustics. So that we have to perform the simulation in the mechanical tools actually. Okay. And then once we perform the simulations, we are having a design explorer option, as Ravi mentioned. We can optimize the different parameters. Suppose if you're having different variables, so we don't know which variable is contributing the what is it, much changes in the performance actually. Okay, so further we have to perform a, DOE analysis to see which variable is having the much higher effects actually. We can able to see, suppose if you're having 10 variables, how each variables are contributing to the output, like output performance actually. Okay, so which variable is contributing more. So like this we can able to identify using the design of experiments tables actually. Okay, so once you optimize everything, then we can go for the validation with the testing, and then we can manufacture the product actually. Okay, so this is the overall workflow for the rotating machinery components. Okay, so Ansys is having a complete platform for that actually. Okay, and I mentioned up to now I covered regarding the flow of any liquid or flow of a gas or some kind of continuous fluid medium actually, or continuous uh, either liquid or gaseous medium. But if you're interested to see the particle level, like how the particles are interacting, how the particle behavior will be there, and how the interaction of the particles will be there, and how the flow of the particles will be there. If you want to analyze the particle level scenarios, so we're having a tool called Ansys Rocky. So this is dedicatedly used for analyzing the particle behavior actually. Okay, so case of cyclone separator case, okay, how the flow is coming and how the particles are getting separated and how the particles are getting settled down actually. So what will be the collection efficiency? So those kind of aspects we can able to really model in the Ansys Rocky, as you can able to see how the particles are entering and how the particle velocity is varying actually. In the similar manner, we can able to see how much amount of particles are leaving the systems and how much amount of particles are leaving the systems are getting settled at the bottom actually. So what will be the collection efficiency at the different particle sizes, that we can able to simulate and see in the Ansys Rocket tool actually. Okay. And similarly, in terms of particle mixing, suppose initially one particle will be there, we are adding another particle. It takes some time. So once you're adding another particle, how the mixing is happening by changing the what is it? Some kind of propeller blades. This is a kind of mixing blades. By changing the mixing blades, how the mixing efficiency has been improved. So whether we are attaining the uniform concentration throughout the tank or not. So that we can able to simulate and see actually. Okay. And in terms of conveyor systems as well. So how the particle has been conveyed actually. In that itself, they're having some kind of heating system as well. So how the heating is taking place, how the heat transfer from the heating coil to the particle is taking place. That we can able to simulate and we can see how the behavior is happening. And similarly, the some kind of particle level breaking, how the breaking of the what is it, medicine capsules will be there actually. And in terms of how the particles are mixing with the waters, and how the mixing phenomena is taking place. As you can able to see by because of the rotation of the blades, how the mixing efficiency has been improved actually, that we can able to simulate using the rocket tools, and we can see the behavior, like all the flow behaviors, like how the velocity variations will be there, how the pressure variations will be there, how the concentrations variations will be there. So all those aspects we can able to see, and we can come to a conclusion whether that is getting our desired results or not. And in a similar manner, we can couple with other physics also. In this case, this is a case of conveying system. So the particles are getting lifted from the conveyor systems, and we are coupling with the mechanical, and we are seeing what will be the stresses that are getting generated actually. Okay, so right now, first thing will be using the rocky. We'll see how the particle lifting is taking place, then it is getting transferred. It's a kind of conveying system. So the particle getting transferred actually. Parallelly, we are coupling with the mechanical, and due to that, we are seeing how the stress variations will be there. So likewise, we can do a kind of multi-physics simulation in a single platform itself. Okay. So that's how this is overall. So just to give a glimpse about the answers of okay. Okay. And next in the overall answers fluid product portfolio. So we are having all the capabilities actually. Okay. Uh, yes, sorry. Uh, we are having a complete product portfolio, as you can able to see. So whenever you're going to perform any kind of simulations, so that will be categorized into three processes actually. One is a pre-processing, and then solving, and then post-processing. So pre-processing in the sense, uh, before going to the simulation, so we have to prepare the CAD as well as the meshing process. So for CAD, we are having a tool called SpaceClay. For meshing, we have different tools as well. For solvers, that is what is the CFD solver in the sense. So Fluent is our CFD flagship product actually. Okay, so where we can able to perform all kind of flow simulations actually. So these are different tools which will be which will be used specifically for particular applications actually. Okay, so maybe I will cover it in the upcoming slides actually. Okay, and post processing will be after performing the simulation, how the results will be there. We have to analyze the results. Okay, so how the variations will be there, that we have to analyze the results using the different tools like CFD post and insights actually. Okay, and if you want to optimize, so we can able to optimize using the optimization tool as well, and we can couple with integrate with the different physics actually, as I mentioned actually. It's a kind of multi-physics platform, so we can integrate the different physics in the workbench platform actually. Okay, so this is the overall outline of fluid product portfolio, and coming into different types of solvers. So Fluent is our flagship product where we can perform all kind of CFD simulation, and the CFX will be exclusively used for turbo machinery applications actually. Okay, so even design of the fan compressors, we can able to do it in the Fluent, but CFX will be the dedicated tool where the kind of flexibility will be there to give the inputs in a much easier way. Okay, so the CFX tool will be exclusively used for designing of turbo machinery applications. Okay, and I already covered regarding the Rocky tool, that is exclusively for the particle level simulation, how the particle interactions will be there. Okay, so it will be based upon the discrete element method actually. Okay, and Forte will be exclusively used for the combustion related application like IC engine combustions. Okay, and how the wherever the clearance of the rotating components will be much lower in terms of gear globe applications. Okay, so over there we'll use the Forte, and we can see how in terms of IC engine application, how the combustion is taking place, on what will be the maximum pressure we are getting generated, and how the spark ignition is taking place. So all the combustion related details we can simulate using the Forte tools. And regarding the Chemkin Pro will be exclusively used for wherever the highly complex chemical reaction is taking place. Okay, so in terms of spacecraft propulsion, so there will be not only one species or two, only two, three species. It's not like that. It's a combination of around some 40 to 30 to 40 species. How the interaction of 30 to 40 species will be there, and how each species are contributing actually, and what will be the reaction rate is happening actually. In order to model the complex chemical reactions, so we are having a dedicated tool called Chemkin Pro. So we will model the chemistry from there, and then we can connect with the CFD, that is Fluent tool, to see the overall behavior actually. Okay, so like this, for modeling the separate chemistry, so we are having a we are having a separate tool called Chemkin Pro. Okay. And the Insight is a post-processing tool. After performing the simulation, how your results will be there to analyze the results. So for that, we are having a tool called Insight. So it's a kind of post-processing tool actually. And we are having a separate software called Polyflow that will be exclusively used for polymer-related application, like how the extrusion is taking place and thermoforming will be there, and how the blow molding will be there. So for that applications, we'll use the Polyflow tool. So Polyflow tool will be exclusively used for polymer-related applications. Okay, and the sensor base will be exclusively used for wherever the ice formation will be there actually. Okay, in terms of whenever the aircraft is flying at a very what I say low atmospheric conditions at a higher altitude, so at the time what will happen due to the low environmental conditions, ice formations will be there actually. So how it is forming on the surfaces of the aircraft or surfaces of the wing, so how it is affecting the performance of the aircraft. So it is wherever the ice formations will be there, how we can how the formation is happening, and how it is affecting the performance. So that kind of scenarios, if you want to model and see the physics change, we are having a tool called Fencer Base. Okay, it is not only on the aircraft; it will be on the wind turbine application also. Whenever we are keeping the wind turbine at sublow atmospheric conditions, so over there the ice formations will be happening on the surfaces of the wind turbine blades. So that will drastically affect the performance, and that will ultimately leads the inertia more actually. And then the stress concentration also will be higher actually. So how it is affecting and how we can able to address it actually in terms of some kind of heating elements, we have to keep it so that the ice will get what is it, de-icing will happen. So like this, in order to simulate the icing phenomena, so we are having a separate tool called Fencer Ice actually. Okay. And I covered regarding the turbo tools as well. So we are having a separate what is it from 2D to 3D, we can able to cover the designing of the blades actually. Okay. And we are having a library as well, where we can able to fetch the whatever the reactions are happening, so that all the libraries will be there in the model field library, where we can able to get all the fluid properties actually. Okay. And we're having a thermal desktop tools that will be based upon the lumped analysis method actually. So for a complete system, how the heat transfer is taking place actually, okay, in terms of designing some kind of uh, thermal satellites actually. Okay, so over there we use the thermal desktop method to see how the temperature distributions will be there actually. Okay. So it's a kind of system level simulation, I can say. So that's the overall idea about the workflow side actually. I just want to cover. So regarding the some of the case studies, I just want to show you. So this is one of the case study on the fan side. So as you can able to see, uh, this is actually the fan blades will be there actually. It will be placed over here actually. Okay. And this is the inlet and this is the outlet area. So we are going to see a different rotation of the fan, how the performance has been improved actually. Okay. So first thing will be what are the analysis we are going to do. First we have to create some kind of geometry actually. There is a CAD part. So we are having a tool called Ansys Space Claim where we can able to create a CAD. Otherwise, you can import from other tools also. It is having a flexibility. Okay, suppose we are creating some in other SolidWorks or CATIA, we can able to import another Space Claim, and then we can able to perform in the meshing in the fluid meshing tools actually. And then we can specify the conditions like what will be the material, what will be either it is a water or some kind of other fluid medium that we can specify the material properties and what will be the condition that is coming in the inlet and what will be the rotation of the fan. So all these things we have to specify in the fluid solver. Okay. So as you can able to see, we are giving the pressure inlet and we are specifying the fan is rotating at 500 RPM. Actually. Okay. And once we perform the simulation, we can able to see how the velocity vectors will be there at the different planes. Actually, I created some center planes, and we can able to see how the variations of velocity will be there. Near to the place, the velocity will be much higher, and surrounding to that, and going some apart from that, the pressure in the velocity will be somehow near to the threshold that is happening. And in terms of velocity vectors, means in order to see where the flow separation is happening, how the what is it? We have to predict what will be the velocity vectors actually. So from there only you can able to see whether any kind of recirculation is happening or not. So velocity vectors will show the direction of the flow particles actually. Okay, direction of the fluid particles actually. Okay, and if some kind of recirculation will be there, the velocity vector will just show the directions actually. It is keep on rotating inside. So like this, we can able to predict in a much easier way. So this is the kind of results of different RPM. We can able to perform the simulation at different RPM, how the flow rate is varying, how the power is varying, actually, that we can able to see. As per the in terms of the flow rate is varying in terms of linearly, but in terms of power, by increasing the fan speed, it is varying exponentially. Actually. So like this, we can able to predict, and we done with the correlation with the experimental data as well. So as you can able to see at 1500 RPM, so the CFD results, the flow rate is coming around some 1470, and the tested results are coming around 1396. The difference will be less than 5 to 10% actually. Okay, we are getting around some 90 to 95% results actually. Okay, closer to the experimental data. And in terms of automotive fuel tank, so this is a complete design also for the automotive fuel tank. So we can able to create the design in the CAD tool, and then if you want to see how the if you are really interested to see the how the designing of the tank will be there, so using some kind of because definitely they have using some kind of extrusion applications, so some kind of blow molding applications will be there. Initially, you can able to see this is the initial plate. They are supplying some amount of pressure. So this is actually the die. So how the because of the blowing pressure, how it is taking the shape of the mold actually. So like this, we can able to see how the material distribution is happening for the fuel tank that we can able to see, and sloshing behavior, how the fuel sloshing behavior that we can simulate using the CFD tools, and we can see in terms of structurally how the stresses are there because of the flow effects actually. And if you're doing some kind of impact analysis, this will comes into the structural part. To drop our impact analysis, we can able to perform in the structural tools actually. Okay. And this is one of the case study regarding the heat exchanger part as well. Maybe I will directly quickly go into that part. So how the heat exchanger performance will be there. Oil is coming from this direction and it is leaving. This is the oil outlet, and air is flowing in this direction. The air inlet, and this is the air outlet actually. Okay, so oil is coming around 100 degrees Celsius, and the air is coming around 50 degrees Celsius. And this is the velocity of the gas around 8 meters per second, and oil is coming at 3.2 liters per minute, I think. Okay. And we are modeling the small component also inside the heat exchanger. So it's not a straight heat exchanger. You can see there are a lot of turbulators they are keeping so that the pressure drop will be much higher, so that the fluid will go in a very slower manner, so that the heat transfer will be happen in a much what is it, much efficient manner. Okay. So the thing will be whenever the oil is flowing inside the heat exchanger, whatever the residence time of the oil will be much higher. So the heat exchange will be taking place in a much higher rate actually. Okay, we are keeping turbulators in the sense that will increase the residence time of the oil, so that the heat transfer will takes place in a much. It will take what is it? Whenever what is it? If it is taking more time for the oil to pass from the inlet to outlet, so the more heat exchange will take place actually. That will be the idea. So for designing the turbulators, we are included the terminator also, even though it is a very smaller thing, thickness of 0.1 mm. So we modeled that part, and then we have done the meshing part as well. We can able to see we are getting the mesh count around 49 million cells actually. Okay, and we perform the what is the meshing, and then once we perform the simulation, and we are getting the expected results actually in terms of how the pressure variations will be there in air side, because there will be two fluid will be there. One is air, another is oil. So in air side, how the pressure changes will be there, that we are checking it actually, and how the variations will be there. At which location the pressure varies means pressure will be higher. We have taken some three different locations: the near to the inlet of the oil, and near to the outlet of the oil, at the center location. So at different locations, how the performance is varying, that we can able to simulate and select. And as you can able to see near to this is the plain one that is near to the inlet of the oil. So over there, the oil temperature will be higher. So maximum temperature of oil is around 97. And as at the center location, the maximum oil temperature has been reduced to 90. Means it is gradually decreasing. 7 degree temperature change will be there. And at the near to the outlet, the maximum temperature is 84.86. So we can able to observe how, with respect to different locations, how the temperature decrement is there. That we can able to nicely predict it actually. Okay. And in terms of from the oil side, how the oil pressure will be there. Initially, the oil pressure is much higher. So as it passes through, the oil pressure is drastically reducing actually, because we are keeping the turbulators. So that will have significant effects in terms of pressure drop as well actually. Okay. And in terms of temperature, how the oil temperature is changing actually. This is the direction of the flow of the oil. So initially, the higher temperature will be around 100 degrees Celsius, and at the outlet, the temperature will be reaching around some 80 degrees Celsius actually. Okay, so like this, we can able to predict the temperature behavior as well. Okay. Yeah, maybe I will just quickly show what are the workflows will be there actually. Okay, I will take just 5 minutes. We it's already we crossed the time actually. Yeah, I will just take some 5 minutes actually to explain the process. So first thing will be this is about some of the example case of the drone actually. Okay, right now you can able to see the CAD geometry. Right? First we have to prepare the CAD geometry. In either in we are having a tool called Ansys Space Clean, where we can able to do a kind of all kind of CAD cleaning process actually. Okay, before going for the simulation, we have to remove some unnecessary components, whatever it is not required actually. Okay, that is not contributing much into the simulation. Wherever the small holes will be there, wherever the small uh, bolt and nuts will be there, that we have to remove. From the CFD purpose, it is not much useful. So we have to remove whatever the unnecessary components. So this is how the space plane GUI looks to be. Okay, so for performing the aerodynamics of an aircraft, so we have to create an outer domain actually. Okay, means we have to specify because the air is going to flow. What is it? Above the aircraft actually. So we have to create some kind of outer domain. So like this, so that we can able to specify this is the inlet area, and then the flow will come like this, and then it will flow over the aircraft actually. Okay, so like this, we have to create some kind of outer domain, and we have to name the inlet outlet like this. We have to give the specifications actually. Okay, so once the if it is a kind of symmetrical body, then we can perform some kind of only create a half body only, and then we will take it for the meshing process. So once the CAD is done, then we'll go for the meshing. So in meshing, this is a fluent meshing GUI looks to be. Okay, as you can able to see, the step-by-step process will be there in meshing. So generally, Ansys is designing nowadays designed in such a way that that will be easy for the new user also. Okay, so generally you don't know where to go and where to select what other things to be done actually. But here it is designed in such a way in a systematic manner. So once the first step is completed, next step will automatically go, and it will highlight whether the process is completed or not by using some kind of symbol icons actually. Okay, if it is completed, then it will show the tick mark, green tick mark. If it is having some issues, it shows in terms of red colors, and automatically if there is an option to right click and see what is the error, and automatically it will show what kind of error it will be. Okay, so in previous cases, whenever during the meshing, so we don't know where the meshing issue happened, wherever the problem happened, so we have to go and debug each and every step. That will take a lot of time. So in order to address that issue, so Ansys now designed in such a way that it will automatically show one by each steps actually, and how the each step has been performed, at which location, at which step the problem has arisen actually. So like this we can able to predict from the workflow itself actually. Okay, so it will allow us to navigate from one step to another step actually. Okay, so it is designed in such a easier way actually. Okay, so once we done the what is it, there is an option to specify the wherever the particular area we have to give some kind of local sensing, we can able to specify. Means some kind of wing leading edge and trailing edge and all, we have to give more refinement to capture the smaller curvatures, right? So where we have to keep very smaller cell size. So like this, we can able to specify it actually, and then we can create a overall volume mesh also. Okay, so we can creating a meshing in the fluid meshing tool actually. Okay. And if you want to capture the how the what is it, how the flow separation is happening. So for that, we have to create some this kind of boundary layers near to the wall, so that it will capture the boundary layer effects in a much easier way. Okay. So that wherever the flow separation is happening, and wherever the in terms of conjugate heat transfer application, how the heat transfer is taking place. So for that, we have to create a boundary layers to see the to predict the boundary layer effects actually. Okay, in a much easier way. And wherever the shock formations will be there, over there also we have to create some kind of more refined sets. And we can able to see at a different we can take some kind of sectional plane, and we can see how the what is it, how the cell how the mesh will be there actually. Okay, and automatically the software will show the criteria of the mesh, whether the criteria has been met or not. If it is not meeting the desired criteria, then we can able to change our settings, and then to get the desired mesh quality. Okay, so that once the mesh quality has been done, then we have to go for the solver part actually. Okay. So now the meshing has been done. We can able to see how the boundary layers has been created near to the walls actually, and after that there are different types of cells are there actually. Right now, near to the walls, the polygonal cells are generated. Away from the walls, you can able to see the hexagonal cells actually. Okay, so right now, previously the triangular and then quadrilateral cells were there. Now the software has been evolved, so we are having a different types of cell types also there, so that we'll get a more accurate results as well as more faster also the process will take place actually when compared to the tetrahedral cells actually. Okay, right now we are having the polyhex core cells. That is the reason cell type. So the hexagonal cells will be created near to the away from the walls, and polygonal cells will be created near to the walls actually. Okay. And once we, this is how the fluent solver looks to be. So once the meshing has been done, next we can go to the fluent solver, and we can specify the properties actually. Okay, and we can specify what will be what kind of materials we are going to use. Either air is going to flow or some other material is going to flow. That material property we need to specify it, and what will be the boundary condition that we need to specify. Once we load it into the fluent, we can check the mesh whether any issues are there or not by using the check options. And then we can specify whether it is a steady state analysis or transient simulation. That is with respect to time you are going to analyze. Then that also we can able to do using the transient simulation. Right now, this case is a kind of steady state simulation. So we have selected the steady state. And what kind of turbulence modeling you are going to use it actually for your simulation. And right now, the material we are using it as a air only. Okay. So by default, we are having a material database as well. We can choose whatever the material you are going to use for your analysis actually. Okay. So this is a kind of compressible flow. They are using the ideal gas formulation. Okay. So in the way we can choose whatever the materials will be. Okay. And if you are interested to model the temperature, then we can enable the energy equation. If you're not interested in terms of temperature, we can avoid it. And the turbulence model, we have to select it actually. So there are a lot of turbulence modeling will be there to model the turbulence effect. So generally it will be KMA-SST model. So we are using KMA-SST model itself actually. Okay. And directly we have to go to the boundary conditions. We can specify what will be the inlet velocities actually. Okay, and what speed the flow is coming. Okay, and what will be the velocity we need to specify, and what will be the temperatures actually. And if it is having some angle of attack, then we can specify what will be the angle of attacks also. If the flow is coming straight, then we can directly specify along the x-axis it is coming. It is one. Otherwise, if it is coming at some angles, then we can specify what will be the angles actually. Okay. And once we perform the simulation, we can able to see how the flow means how the flow behavior will be there. That we can able to analyze using the post processing tools actually. Okay. So we can able to see we are giving the flow at some certain angle. So we can able to see the flow is coming at certain angle and we are hitting the wing, and how we can able to see how the recirculation zone is created near to the particular area. Okay. Uh, so those kind of how the flow separation is happening, at which location the flow separation exactly happened, and what will be the pressure variations will be there actually across the wing. So that all those aspects we can able to analyze using the post processing tools actually. And we can able to see with respect to different angle of attacks how the drag forces will be there and how the lift forces will be there. So that we can able to plot and we can able to see. So we can able to see as the angle of attack increases, the lift force has to increase as per the. So this is the stall area. So after stalling effect, the lift force has to decrease actually. So we can able to see for this configuration we can go up to maximum angle of attack 10 degree. So like this we can able to design. We can able to have a constraints also from the simulation. We get to know what will be the constraints will be. So that's the major thing I just want to cover it from my end. Uh, um, yeah, if you have any questions or if you have any doubts, you can please put it in the chat box. And if you're interested to explore any of the particular topics, you can please send us a mail. So we'll be happy to connect and we'll discuss only on the specific particular what is it, whatever the application you are working on. We'll have some kind of detailed discussions and some kind of detailed presentation regarding those aspects as well.